Hi, good afternoon. Welcome to this CIS network seminar. I'm very happy to announce our first speaker from EDIAB today, Dr. James Henderson. James is a senior researcher at EDIAB Research Institute, where he leads the Natural Language Understanding Group. His talk today is titled Understanding Language as Bayesian Inference of Bayesian Representations. Just to give you an idea of what to expect today. So we have 1 hour. I was informed the talk will go 40 to 45 minutes. We then have time for questions. The speaker also agreed to take questions directly during the talk. So don't hesitate to put them either in the chat or raise your virtual hand or the hand in the room if you're around, and we try to address them. So a big thank you, Dr. Henderson, for joining us today. And a big thanks to the team for organizing this event. And now, James, the floor is yours.
Yeah, so I'm going to talk about natural language understanding as Bayesian inference of Bayesian representation learning. This is work in collaboration with Fabio Fair and other members of Natural Language Understanding Group at IDIAP Martinique. So we've all heard of large language models like ChatGPT, had a big splash recently. They are really surprisingly effective models. They not only model language very well, they very rarely make any grammar mistakes or anything like that. They also seem to have the ability to model abstract semantic concepts. They generate coherent texts. They respond in a coherent way to prompts. And this is partly because they've been trained on very large models that have been trained on very large amounts of data for a very long time. But partly it's because they're all using the transformer architecture. So this is an architecture that's just been introduced a few years ago. And the key difference between this architecture and previous architectures is the use of attention. So we see there are these columns of feed-forward networks, one for each position in the input, but the way information is mixed across these positions is with attention. So self-attention in the encoder, self-attention in the decoder, and cross-attention between the encoder and decoder. And that's crucial to the way these models work. And these models really do work very well. They seem to have learned abstract semantic generalizations, and yet they've never been trained on semantic annotations. Nobody has ever told them what the meaning of a sentence is. The only thing they've ever been told is to predict the next word given the prefix of previous words. Objectives like that are very superficial, and yet they capture this underlying meaning of the text. And that can only happen because they have an appropriate inductive bias. They can generalize from the superficial characteristics to the abstract concepts because of the inductive bias. So where does that inductive bias come from? We think it comes from the latent representations, the hidden space of the transformer. So looking specifically at the latent representations between the output of the encoder and the input of the decoder, this is a sequence of vectors. So vectors are good. We can induce lots of meaningful features. The number of vectors in that sequence can grow with the length of the sentence, which is really crucial for natural language text because we want to be able to handle very large texts. And those sequence of vectors is then interpreted by the attention function. So to understand what the structure of this latent space is, we need to understand the way in which these sequence of vectors are being interpreted. So we'll argue that these latent representations are being interpreted as Bayesian representations in that they are probability distributions, in particular mixture distributions. And we can generalize this concept to any mixture distribution. We also argue that the computations that are being performed by the transformer are a form of Bayesian inference. So again, they're behaving in a probabilistically well-defined way, or approximating that. We show that by proposing a variational Bayesian framework for modeling attention-based representations, which uses Bayesian nonparametrics. And we show that when we improve the approximation, we get better representation. So suggesting that this is the underlying reason for the improvement for the appropriate inductive bias of transformers. So in the rest of this talk, we'll make 4 main contributions. One is to analyze the nature of these attention-based representations to understand them better. The second one is to propose this variational Bayesian framework for learning these attention-based representations. We'll talk about what that is. And thirdly, more specifically, we propose a variational autoencoder for transformer embeddings, and that show that this model learns effective, smooth, and sparse latent representations. And lastly, I'll talk about some very recent results on reinterpreting pre-trained transformers to get at what these large language models are in fact learning empirically. So I'll have a different section to talk for each one of those contributions, starting out with the nature of attention-based representations. So what is attention? So the output of the encoder is a sequence of vectors. That's these Z's here in the formula, ZIs. The decoder then accesses this representation by issuing queries, and then the attention function returns, and the result of the attention function is a vector. And that vector is a weighted sum of the vectors that are being paid attention to, where the weights are determined by a softmax function applied to the similarity between the query and the vector, which is measured with the dot product here. So the first thing to note about this attention function is its permutation invariant. It doesn't care about the order in which we list these vectors Ci. So it's a set of vectors. It's not really a sequence. It's being interpreted as a set. So we can just draw these points in two-dimensional space here, just list the set of points, and that's enough to specify our attention function. The second point about the attention function is it's imposing a normalized weighting over these vectors. The attention weights here are normalized to softmax, it sums to 1. So it's not really treating them as a set either. It's treating them as a distribution over vectors because the heights of these sum to 1. So we're showing that by taking each point in our two-dimensional space and sticking an impulse distribution at each one of those points. Thirdly, we don't know ahead of time how many of these points we're going to have because it depends on the length of the input text. And their input texts don't have any particular bound in general. They can be arbitrarily large. So we need to account for the possibility that there could be any number of vectors in this sequence of vectors. And those 3 properties are exactly the properties of nonparametric space of mixture distributions. So it's nonparametric, meaning that there's no finite number of parameters that can specify the whole space. If we tried to pick a finite bound, there would always be a text that's bigger than that, and we would need more parameters than that to describe all the vectors. So it's nonparametric in that sense. And it's a mixture distribution because we have this normalized weighting over the the vectors, and there's one component of the mixture per vector. More specifically, we argue that transformer embeddings are nonparametric mixtures of impulse distributions like we're showing here. And if we make that assumption, then we can define attention, we can redefine attention as Bayesian query denoising. So how does that work? We take the vectors, we map them to this mixture of impulse distributions, and we say that's our prior over vectors. Now we get the query, and we interpret that as a noisy observation by sticking Gaussian noise around the point of the query. If we have this prior and we see this observation, we compute a posterior, and we set up the heights of that prior such that when we compute our posterior, we get exactly the result of attention. So these attention weights are exactly the probabilities we get from the posterior after computing this Bayesian denoising. And then we take the expectation of that, and that's exactly the result of the attention function. So we can rewrite the attention function as Bayesian query denoising. We're given a prior and an observation, and we return the expected value of the posterior. So that's denoising. We've replaced the sequence of vectors with a prior distribution. We've replaced the query vector with a noisy observation, and we've replaced the resulting attention vector with the expected value of the posterior distribution. So this is wonderful because it helps us understand what's going on with attention, but it also allows us to generalize beyond mixtures of impulse distributions. Query denoising is perfectly well defined no matter what the prior is. And so we can use any mixture distribution as our prior and still define denoising attention over that prior. So for example, we can use a mixture of Gaussians like is shown here. We take that mixture of Gaussians and interpret it as a prior. We interpret the query as a noisy observation, and then it's easy to compute the posterior because the multiplication of two Gaussians is a Gaussian. So we can compute the posterior and its expectation. And we have a perfectly well-defined notion of attention over a mixture of Gaussians. So to summarize, we've argued that attention-based representations should be modeled as mixture distributions because it's exactly equivalent. The set of vectors can just be mapped to a mixture of impulse distributions, and the attention function can just be replaced with query denoising. Also, we can generalize to any mixture distribution. So now instead of our set of vectors, each vector gets mapped to a component of the mixture, and then say a Gaussian, and then we do query denoising with that mixture of components. So this is a powerful generalization of the attention function and their representations. Okay, so now that we've understood the attention, latent representations of attention, we've captured these three properties and generalized to any mixture distribution, we can now in a position to define our variational Bayesian framework for attention-based representations. So first, a review. Variational Bayesian approaches, it covers a wide area, but I'll talk specifically about variational autoencoders, where it's an autoencoder, so you're taking some input, encoding it in a representation, and then decoding to try to reconstruct the input. But the latent space is regularized by variational information bottleneck. So here, our latent space is just a vector space. The encoder outputs distribution over vectors. We sample a single vector, and then that single vector is an input to our decoder. So this is the standard VIB. And the way VIB works is this sampling step here adds noise, and noise erases information. So that amount of noise that we add controls the amount of information that comes through. The reconstruction loss is trying to push more information into this representation here. And there's a KL divergence with respect to an uninformative prior that's trying to increase the amount of noise to reduce the amount of information. So there's this trade-off between the regularizer trying to push the amount of information down, reconstruction loss trying to push the amount of information up, and you end up with a bottleneck that only lets through exactly the information you need and not any information you don't need. So that's VIB. Now we want to build a VIB for transformers. So here we're no longer dealing with a vector space. We're now dealing with this space, which is a mixture of impulse distributions. And we can define distributions over this space using the theory of Bayesian nonparametrics. So it tells us how to define distributions over mixture distributions, and it answers questions like how to sample from those distributions, what is the mean, how do you do inference of posterior? And so I'll go more specifically, not in too much detail, but more specifically about that. So we propose to use Dirichlet processes as the representation of the prior and posterior. When you sample from the Dirichlet process, you get a mixture of impulse distributions. Then that mixture can be accessed using denoising attention by the decoder. And so this sampling step adds noise to this posterior distribution so that you only see some information about the posterior via these vectors that are sampled. At test time, we don't want to add noise. There's no reason to add noise at test time. We want to use the mean of those samples. And the theories of DPs tells us that the mean of this distribution over distributions is the mixture of Gaussians that define the base distribution, the thing that we're sampling these vectors from. But as we just saw, we can equally well apply denoising attention to this mixture of Gaussians. So from the point of view of the decoder, it's looking at a mixture of Gaussians instead of looking at a mixture of impulse distributions, but it looks just like a typical example of what it was trained on. So that's really interesting. Third thing we use about from the theory of Bayesian nonparametrics is that Dirichlet processes are conjugate prior. That means that if you have the prior and you have a set of observations, there's an exact formula for the posterior. So we have the encoder output a set of pseudo observations and then use this formula to infer posterior. So just to go into a bit more detail, the encoder outputs one vector, a transformer encoder outputs one vector per token that's input in this input sentence. Each one of those vectors gets mapped into a pseudo observation, which is the parameters of a Gaussian and a pseudo count, like this one here. Also, the prior is of the same form. It's a Gaussian and a pseudo count. Inference then is just we compute a mixture of all those Gaussians and we sum all those pseudo counts, where the mixture of Gaussians is weighted by the individual pseudo count associated with each Gaussian. One term for the prior and the other terms for the output of the encoder. So very simple way to infer the posterior Dirichlet process. To complete our definition of nonparametric variational information bottleneck, we needed to do some approximations. First of all, we needed to come up with a meaningful KL divergence between the posterior and prior Dirichlet process to regularize the posterior. And secondly, we needed to come up with a reparameterization trick for sampling from the posterior in a way that when you backprop the reconstruction loss you can backprop through that sampling step effectively. So that's what the reparameterization trick in VIB is all about. And we came up with one of those. An interesting property of this KL divergence regularizer is it gives us sparse representations, okay? The encoder is outputting a pseudo observation for every input token. But those pseudo observations all have a pseudo count, and the KL divergence is regularizing the total of that pseudo count. So by pushing down the total, some of the individual pseudo counts get pushed to zero. And as soon as the pseudo count gets pushed to zero, the weight of that component goes to zero, and it's like that component doesn't exist. So it gets removed from the posterior distribution. So the actual posterior is sparse with respect to the number of inputs. It has fewer components in it than the number of tokens that are input to the encoder. So to summarize this, the NVIB is acting like a VIB regularizer. It's only allowing information to pass through it that is needed for reconstruction and regularizing out all the other information. Sampling these mixtures from the posterior means that you're only getting a noisy image of the posterior, and essentially the amount of noise depends on how many samples you're selecting from this space distribution, and that's regularized by the total pseudo count, which is why that has decreasing the total pseudo count increases the noise because you're just seeing less of the base distribution. Right. So now that we have this NVIB regularizer, we can use it to build a variational autoencoder for transformers. So it's a VAE, we have an encoder, we have a decoder. The encoder is a transformer. The output of the transformer is a set of pseudo observations that go into an NVIB layer. The NVIB regularizer controls the information that passes through that latent representation, and then the decoder uses denoising attention to access that latent representation. We train this as an autoencoder, so we have a cross-entropy loss for reconstructing the sentence on the output. We also have losses for the KL regularizer, which is the one that pushes the information down by making the posterior more similar to an uninformative prior. And then we have a set of hyperparameters that balance these different losses. So we have a hyperparameter that weighs the reconstruction loss versus the Gaussian part of the KL divergence. So trying to make sure these Gaussians aren't too peaky. And another weight for the regularizer for the total pseudo count, which is the one that tells us how many vectors we're getting at the end. So by tweaking these hyperparameters and a couple of other hyperparameters I'm not talking about, we're able to vary the sparsity of the latent representation. At one extreme, we're keeping all the vectors, and we can very easily reconstruct the sentence. At the other extreme, we're just keeping one vector, and we can't really reconstruct the sentence. In the middle, we can drop up to half the vectors and it has no impact on the reconstruction loss. Even at 2/3 of the vectors dropped, there are models that can perform very well. we compare this to two baselines, two extremes. One is where we take the output of the transformer and pool it into a single vector and then just have a normal VIB regularizer in a single vector space. That one, just not enough information. It can't really reconstruct effectively if you compress it down to one vector. The second one keeps all the vectors. There, every vector that's output by the encoder has an individual VIB regularizer on that vector, but you always have n of them. And that one very easily reconstructs, but has to keep all the vectors. The NVIB, we can adjust, as we just saw, the hyperparameters to get some sparsity, drop some of the vectors, and it still reconstructs perfectly well. So in addition to, in addition to being able to reconstruct, we want these models to learn a meaningful latent space. So for example, we want it to be a generative model. If we sample from the prior and then put that sampled latent representation into the decoder, we should get a meaningful sentence out. So when we keep all the vectors, as we saw, the reconstruction is fine. If we sample from the prior and look at the distribution of generated sentences, it does a good job of covering the whole space of the distribution of sentences it was trained on. But if you look at the individual vectors, often you sample from the prior and that individual vector is actually not a good vector of language, example of English in this case. So that's shown here. The forward perplexity is bad, is too high for this model that keeps all the vectors, whereas the NVIB regularizer reconstructs well. There are models that cover the space well and generate good sentences all the time, as well as being able to reconstruct well. We also looked at the smoothness of the space by doing interpolation. The idea is you take two sentences. Sentence one, you put it through the encoder and get a point in latent space. Sentence two, you put it through the encoder and get another point in latent space. Then you interpolate between the two in latent space, and then take that point and generate a sentence from it and look at that sentence to say, what's it like? On one extreme, you get something that's exactly the same as sentence two, and the other extreme, you get something that's exactly the same as sentence one. In between, well, for the model that keeps all the vectors, again, we end up with holes in the latent space. The sentence that gets generated in between has basically nothing to do with either sentence one or sentence two. It's not a smooth transition from sentence one to sentence two. Whereas when we generate from the interpolation for NVIB, we get things in the middle here that are similar both to sentence one and to sentence two. It's a smooth transition between the two. So that shows that the latent space is smooth. We're moving around it smoothly. Also, one of the reasons for this is that the way we do interpolation is in some sense much simpler, right? So in these models that use sets of vectors, if you want to interpolate between sets of vectors, you have to do some kind of alignment and then interpolate between the aligned vectors. And that doesn't work very well. If with NVIB, we are not dealing with sets of vectors, we're dealing with distributions. Interpolating between distributions is easy. You just do a weighted sum of the two distributions. And then you decode from that weighted sum. And that works incredibly well. So that is just kind of another example of why changing to a latent space that's a distribution over vectors instead of a set of vectors really helps a lot in understanding what you're doing in these deep learning models. Okay. So to summarize those results, we trained an NVIB on text. We get a better latent space, a better representation of text. It has an appropriate number of vectors so that we're getting some compression. It generates the distribution over text more effectively. And when we interpolate, it gives us smoother interpolations. All these models we consider can be thought of in some sense as approximations of nonparametric Bayesian inference. But the NVIB model is a better approximation than the variational transformer that keeps all the vectors or the one that's pooled. So we argue that better approximations gives us better latent representations. So that's suggesting again that the reason why transformers are working is because they're trying to approximate nonparametric Bayesian inference. So in the last section, I just want to talk about some very recent results where we're really testing that. When you have a transformer that's already been trained, so a pre-trained transformer like the ones we talked about at the beginning, can we reinterpret that in terms of this theory and say something about it? So that we can do because, as we saw at the beginning, attention is equivalent to query denoising. So we can, that's a constructive proof. So we know exactly how to take the parameters that are used in attention and map them into parameters that give us the same function for denoising attention. Then we just need to deal with the fact that, we're not actually the encoder is not outputting this mixture of impulses, it's outputting a Dirichlet process. So we need to have that Dirichlet process have low uncertainty. We make the Gaussians very peaky and we make the pseudo counts very large. The last thing we do is we model the prior on the distribution, empirical distribution of vectors. We take the encoder, run it on the training set, look at the distribution of vectors over all the senses, over all the positions, fit a Gaussian to that distribution, and that's our prior. So after that, not surprisingly, we get exactly the same behavior. There's a little bit of noise, but it doesn't affect anything. The model still behaves exactly the way we expect. We get exactly the same predictions from this NVIB model as we got from the pre-trained transformer. So it could have been that just adding that, because we can't have infinite pseudo counts, so just a little bit of noise might have broken things, but it doesn't. In fact, we can add a lot of noise and it doesn't break anything. We take this initial model and move in the direction that the regularizer wants us to move. So we add uncertainty. We make our Gaussians fatter. We make our pseudo counts smaller so that the model has more uncertainty. But there's no training here. We're just, all the models that are taken from the pre-trained transformer are still exactly the same. The only thing we're changing is the hyperparameters that are used to map from a mixture of impulses into a mixture of Gaussians, or into a Dirichlet process. And so we can add this uncertainty. And the really surprising thing is sometimes it actually gets better, which we're doing a kind of post hoc regularization. We're making the model smoother, making it more like an NVIB model should be, and sometimes it gets better. So this is the results for machine translation. We take the source sentence, encode it, put a VIB layer on that encoding, and then the decoder generates the target language. We see that for French to English, we get a very slight improvement. For German to English, we also get a slight improvement. For Romanian to English, we get a very slight degradation. But the really surprising thing here is that it basically doesn't make any difference. The model behaves, it changes its predictions, but the quality of the model basically doesn't change. When you add more uncertainty, it doesn't change anything until at some point, all the information is gone and the model collapses. It can't do anything. So that's what this drop here, it goes down to virtually 0 blue score because it's just lost all of the relevant information all at the same time. So what does that mean? It means that this is a really well-calibrated model of noise. It's not dropping this feature and then dropping that feature and then dropping that. All the features disappear all at the same time. It's a really, really surprising result. I mean, it's not a lot of results, but this is really work in progress, and I'm really excited about it. So what does that tell us? Well, it tells us that, for one thing, NVIB can capture the relevant information. The information that a pre-trained transformer learns about language can be captured in the parameters, even when we add noise. The second thing is the regularizer removes information that's not learned. It's not removing information that the pre-trained transformer needs. At some point, all the information is gone and things collapse. But in the meantime, it is removing information, but it's not information that the decoder cares about. So it's a really good model of what the pre-trained transformer has not learned. So that means it's a really good model of the inductive bias of the pre-trained transformer. And because this is a good model of language, it's a really good inductive bias for natural language. I think that this shows that NVIB is really a good model of the inductive bias we need to train language. Okay. So, of course, now you're going to say, why don't you train very large models on very large amounts of text for a very long time? The answer is money. But we'll hopefully have a chance to do that. Right. So, to conclude, we've argued that attention-based representations are nonparametric mixture distributions. We've used that fact to propose a variational Bayesian framework for attention-based representations with its NVIB regularizer using Bayesian, the theory of Bayesian nonparametrics. We've shown that the resulting nonparametric variational autoencoder induces latent representations that are effective, smooth, and sparse. And we've shown that this NVIB model captures the kind of information that is in practice learned by pre-trained transformers. More generally, NVIB is combining, it's a way to combine the advantages of transformer with the advantages of variational autoencoders, and the resulting inductive bias we get is a good inductive bias for modeling language. So just to finish up, I wanted to go back to the original question, why do transformers work so well? So we've argued essentially that the reason transformers work well is because they're nonparametric variational Bayesian models. The latent representations are nonparametric mixture distributions. The encoder is doing a kind of nonparametric variational Bayesian inference. The decoder is approximating nonparametric Bayesian generative model. But it kind of begs the question, if that's what the transformer is doing, why is that good? Well, it could be just because nonparametric Bayesian inference is just super powerful. It can do anything. Give it enough data, it can do anything. So that could be. We've argued that it's actually more than that, that it's an appropriate inductive bias for natural language. If it's an appropriate natural language bias for natural language, we know, well, we hypothesize that language is isomorphic to thought because anything you can say, you can think, and anything you can think, you can say within some approximation. So the structure of thought is somehow the same as the structure of language. We've shown, we know that transformers are very good models of language. We've shown that transformers are modeling Dirichlet processes. So it's natural to conclude that transformers work well because thoughts are Dirichlet processes. It follows, right? So this might require a bit of future work to conclude that definitively, but that's kind of the line we want to go. So I've talked about natural language understanding as Bayesian inference of Bayesian representations. And if anybody has any questions, I'd be happy to answer them.
Very much. Any questions on site or online, please?
Thank you for the very interesting talk. I don't know how this kind of things work, but at least I know in ChatGPT, you write something, you get a response, and you can write something back, and it will remember that first input. So I wonder, like, how this modeling latent space with distributions rather than a mixture of impulses would help for sequential input.
Well, it's, I mean, the way the model works is, well, we don't know exactly how the model works, so they're not telling us, but it is underlyingly a transformer. And that means basically this sequence here, the sequence of inputs, is not just one turn or one sentence. It includes a very long history. And so it's using the attention mechanism to look back at those previous parts of the history of the input. And that's how it maintains a coherence. It's just using that as a kind of memory so that it can always access those old representations.
It's like using all those text as an input.
Yeah, everything is an input.
Maybe having a distribution rather than
Yeah,
impulses can help in terms of memory constraints.
absolutely. Yeah, that's but there is some work on of doing very large scale attention by approximating the distribution as a mixture of Gaussians instead of a list of vectors. Yeah.
Not sure if I got the main difference between one of the main differences between the transformer, pure transformer, and NVIB is the noise injection that you have done.
Yeah.
So shouldn't this part affect the generalization of the pure transformer in some of the tasks?
Yes, it should. I mean, it should improve the generalization. That's something we haven't tried yet. So in particular, this one here, previous work has shown that a normal VIB regularizer helps when you're generalizing out of distribution. That you're trained on one distribution and then you get test set that's slightly different. It's a little unexpected. There's a tendency for deep learning models to specialize to the training distribution, and then when you change the output to a different test distribution, performance crashes. VIB regularizer improves that generalization. So we want to do these same experiments out of distribution and hope that we get a boost. So that's the kind of thing you would expect to exactly right.
The question on site online is to appears there are no questions. That's fine. Speak again, please. Just some brief words of closing. Thank you so much, James, for the talk today. Thanks to all on-site and online. It was great having you. Just some heads up, you might have heard that this weekend, so Saturday, Sunday, they're the EPFL Open Days. There's a lot going on. Please pop by. We have some workshops, we have a booth, and there are roundtables organized by CIS. Then on Monday 8th, we are looking forward to welcome Professor Michael Herbst for our Get to Know Your Neighbor seminar. On 15th May, we have our next CIS network seminar with Dr. Sebastian Marcel from IDIAP. And on Monday, June 12th, we have the Get to Know Your Neighbor seminar with Professor Brian Ford from IC. Thank you so much, and we hope we see you soon again. Goodbye.